Okay, so here's part 2 for our energy review guide. In a problem like this, and you see that we will provide you with an organizer. What I'm also going to do is you can do this if you want, or you can completely use a different organization method as long as you show one. I'm going to add the specific heat capacity as a variable because that is a variable that we have in our equations. Joules per gram degrees Celsius in this case, and so that is C in our MCAT equation. And so what we are going through is a piece of metal is being added to water, and so whenever I see the metal and the water interacting with one another, I know that I have to set up a negative Q equals Q calculation, because if I know that I'm dealing with both of those objects, then they are interacting with each other, and I can use the law of conservation of mass, or the law of conservation of energy, to say heat lost by the metal is equal to the heat gained by the water. And with this being said, heat loss is negative Q, so that's of the metal, is equal to positive Q of the water, because that is heat gain. And what I know about the variable Q, or heat energy, is that I can calculate it using MCAT, right? MC delta T. And so I'm just going to expand on both of those and just say that, well, negative Q is negative product of mass of our metal, because this is the side that's losing, which is our metal object, a specific heat of the metal, and the change in temperature of the metal. And that's equal to the mass of the water. Right? This side's positive because heat is being gained, specific heat of the water, and the change in temperature of the water. All right, so now we are going to plug in our values. We have 92.9 grams for our metal. We have 178 degrees Celsius is the initial. The mass of the water is 75 grams. That could have been milliliters as well. It is initially at 24 degrees Celsius. They reach thermal equilibrium, which is the same temperature of 29.7 degrees Celsius, because they are both now together in the same space. And I can calculate the changes in temperature there. So this one will end up being negative 148.3 degrees Celsius. This one will end up being about 5.7 degrees Celsius. The metal specific heat capacity is what we are looking for, and because it does not specify, we can use whichever specific heat value for our water, and that is going to be 4.18 joules per gram degrees Celsius. Now, where do I plug everything in? Well, on my metal side, let's say that I have my metal side is all of my green highlighted. I know I need the mass, I need the specific heat, and I need the change in temperature. And so those are what I'm going to plug in on that side. And for the water, I'm going to do the same thing, have MC delta T for the water. And I'm going to plug my values in. Remember, the initial and finals are just so that we can get those changes in temperature of each substance. And then I am going to just highlight that there as well. All right, so the negative just represents heat lost, 92.9 grams. We do not know the specific heat. We do know that we changed temperature by negative 48.3 degrees Celsius. We have our 75 grams, 4.18 joules per gram degrees Celsius, and 5.7 degrees Celsius temperature change. What you notice is that the negatives will cancel each other out every time. Therefore, if you want to just go ahead and kind of ignore those negatives in terms of the math itself, it'll work out just fine. So we have our 13,777 times x equals 178 or 1,786.95. We divide by what's being multiplied to the variable to get the variable by itself. We should end up with an X, or a specific heat value for the metal, of about 0.129 joules per gram degrees Celsius, which means that we can come up here to our specific heat table and we can identify that, hey, that is lead, right? Because it's so close there. And so we know that this is lead. So we have not just calculated the specific heat capacity of the metal, but we've also been able to use that to identify what the identity of the metal is. Down here, this is going to be the a problem similar to our Cheeto burning in our fume hood, heating up the water. And so we're calculating the amount of heat energy by the water. Now, the difference between this is, even though the idea of heat loss and heat gained is existent here, what we're asked for is specifically the heat of the water. Therefore, we are just looking for Q of the water. How do we find Q? Well, we need the mass of it, or the sample size of it. We need to know our specific heat capacity, right? How easily or difficult it is to change the temperature of our water, and the overall change in the temperature of the water based on that marshmallow burning here. And so we're going to use, we have two objects, but we're talking about water here specifically, so all information for water. We're looking for the energy that the water gained. The mass of the water is 50 grams or milliliters. The initial temperature was 20, and the final temperature was 35.5. So 35.5 minus 20 gives us 15.5 degrees Celsius as a change, and it tells us that we want the energy in calories. Well, we know that the specific heat capacity for water is 4.18 degrees, or 4.18 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. And because I am looking for calorie as my energy unit, this is the specific heat value that I am going to use. And so I will put in 1 calorie per gram degree Celsius. And now we just calculate Q. Q is equal to mc delta T. Q is, the mass is 50, C is 1, and change in temperature is 15.5. Therefore, the energy that is gained by the water is going to be about 775 calories. So that is how much energy was absorbed by the water. So there's our answer. That positive answer, because the temperature was raised from start to finish, means that heat was gained by the water. And so we come here, assuming all the heat released by the burning marshmallow was absorbed. How much heat and calories did the marshmallow lose? Your initial instinct is going to want to use Q equals mc delta T again. However, knowing that heat lost equals heat gained, we figured out how much heat was gained. Therefore, that's the exact same amount that was lost by the marshmallow, right? If we're assuming all the heat was gained by the water and it came from the marshmallow. Therefore, we don't have to do any math here. The only change is we would say negative 775 calories, right? And that is because heat was lost by the marshmallow. So the value itself is exactly the same. The only difference is that negative sign, because it was released by that marshmallow. So hopefully these videos help. And as always, if you have any questions, always feel free to reach out. All right, see you later.